So section 2.2 in the text is titled Vector Operations. What it's about is showing you two different approaches to add and subtract vectors graphically. The first concept in this section is the idea of vector scaling. So overall, we're going to talk about three different ways in which vectors can be multiplied. The first, vector scaling, happens when you multiply a scalar by a vector, just as it sounds. The key point that you want to realize is when you do that, you're going to get another vector. And that vector will have a very close relationship to the original vector that was scaled. Particularly if we take some scalar k and we multiply it by a vector a, we know that the new vector will have the same line of action as the original vector a, and its magnitude will be scaled by k. So if you notice, that kind of sounds like a weirdly long definition there. I'm not talking about its direction explicitly. I'm talking about its line of action. And why is that? Well, as long as the scaling factor is positive, the direction won't be changed. However, if the scaling factor is negative, the direction will be rotated by 180 degrees along the line of action of the original vector. If the absolute value of the scaling factor is greater than 1, that will tend to increase the magnitude, and if it's less than 1, that will decrease the magnitude. And visually, this is a lot easier to see than to explain. Here I have a vector a. When I scale by 2, since 2 is positive, direction remains unchanged. And since 2 is bigger, has an absolute value that's larger than 1, that increases the magnitude. Key point to note, when I scale by -1, that doesn't change the magnitude, but it just rotates the vector 180 degrees about the line of action. And we can kind of combine both that redirection or multiplying by a negative along with scaling. And in this particular case, they've multiplied by -0.5. The negative rotates the vector 180 degrees. The 0.5 decreases the amplitude, the magnitude of the vector by half. So vector addition, the parallelogram rule, this is probably not the way that if you've already been taught this material, that you were taught it. It's kind of a bit of an archaic approach to do it. There's a much simpler way that we'll see on the next slide. But if you're going to add vectors through the parallelogram rule, particularly A and B, you'll notice that it's a three-step process. So just to kind of refresh our terminology, the book weirdly goes to using the idea of tip and tail again for a vector. Where the arrowhead stops, that's the tip, and where the opposite side of the arrowhead is called the tail. So to add by the parallelogram rule, we start by adjoining the two tails together, which they've done here. We'll draw a line that's parallel to each of the two vectors that starts at the tip of the other vector. So this line is parallel to B, and it starts at the tip of A, and vice versa for this line. If you notice, these two lines will intersect at some point, and if I take the line segments from the tip to the point of intersection, tip to the point of intersection, along with view the two original vectors as lines, naturally what I get here is a parallelogram. And we'll define the vector sum of A and B as a vector that goes from kind of the common point of the tails to that point of intersection. So that is denoted as R, again, just to reemphasize the fact that when you add vectors, you often call the sum the resultant vector. So that's how you do the parallelogram law. And think of what a pain it is to just describe, and if you had to draw it, it's not too bad. But what if you actually had to physically determine some parameters of this resultant, its magnitude and its direction? You're going to have to apply a lot of geometrical principles that you maybe haven't done in a while, that you would have to dust off. And in general, it's just not going to be a very convenient approach. So both of these graphical techniques that we're talking about, they're good to build some physical intuition, but they're not very valuable from an analysis point of view. Triangle rule is what you're probably familiar with from your mathematics courses. It's just the idea of adding vectors in a tip-to-tail fashion. So if I want to add vectors A and B, what I do is I take the tail. One way I could do it is to take the tail of B and put it on the tip of A, and then draw a vector that completes the triangle that goes from and this is where the idea of tail to tip comes in, from the tail of A to the tip of B. So I just kind of close that triangle. Since addition, vector addition, scalar addition, whatever kind of addition is in general a commutative property, it's not surprising that I didn't have to put the tail of B on the tip of A. I could have placed the tail of A on the tip of B. And in both cases, even though the drawing is kind of a reflection of one another, the resultant vector is the same. And that's why, as I mentioned in the prior slide, the parallelogram rule is redundant, because if you take and you place this triangle rule addition, if you draw it directly on top of the other triangle rule addition, you'll see that it forms a parallelogram rule. So That's the kind of idea of redundancy. In the parallelogram rule, you actually have two examples of the triangle rule right on top of each other. How do you subtract vectors? Well, when you subtract numbers, you just add the opposite, which is to say you make the second number negative, and you just use all your usual addition rules. So we're going to do the same thing for vectors. However, remember that making a vector negative or scaling by -1 doesn't change the magnitude, but it rotates the direction of the vector 180 degrees along the line of axis. So if I want to subtract b from a, the first thing that I would do is scale b by -1, and then I would take that new vector and I would just follow my geometrical rules for adding it to a. So I could do the parallelogram rule or I could do the triangle rule. In either case, that would give me the difference of a and b, or a minus b. The idea of the resolution of forces, as the book calls it, is just breaking a force into the sum of multiple forces. Now, why would we want to do that? Well, the book kind of introduces this concept from a physical or practical perspective. What if we had two rods and they were joined at some pin, and we were interested in understanding what's going on internally in these rods? Are they being compressed? Are they being stretched? How will we find that? Well, as we'll see when we get to that point in the text, what we need to do is define the component of the force that's coaxial to that actual rod. So what component of the force is actually aligned or acting upon that rod? So in this case, the rods themselves kind of define coordinate axes for which we'd be interested in writing the resultant force acting on the pin as the sum of two forces which are aligned along those coordinate axes. So that's a lot of words, but hopefully you see graphically what's going on. I'm interested in knowing the force that's acting along the direction of this rod and this rod. So I draw coordinate axes which are aligned with the two rods, and I kind of, in a reverse fashion, that's what your book says, decompose, which is a more common word, this force into the sum of two forces which are aligned along my axes of interest. Now, kind of to foreshadow a little bit, I'll go back before I do this example problem. This will become a very, very valuable tool when the two axes of interest are perpendicular to one another. So that's not always the case. Like here, geometrically, we just happen to be interested in knowing the components of the force along these specific axes. But in general, if we can make those axes perpendicular, we can kind of turn vector addition into scalar addition. Because as we talked about in the prior learning module, when two vectors are co-aligned, the vectors add by simply adding their magnitudes. Wanted to do just a very quick example problem from this section. Specifically, what we're asked here, we're given this diagram, and we're said which of the following is the correct expression for r in terms of f1 and f2. Well, you might be tempted to say, oh, that's just a triangle rule, right? So that means that r must be f1 plus f2. But remember, the triangle rule has one particular requirement. You have to put the tip of one vector onto the tail of the other vector. And if you notice the two vectors that you might think you're adding, f1 and f2, they don't have a tip-to-tail arrangement. In fact, it kind of looks like what someone is trying to do is add f1 and f2 according to the parallelogram rule. But if they were adding them according to the parallelogram rule, the resultant wouldn't go on this diagonal. It would go on the diagonal, if you recall, from the point at which the two tails adjoin to the point of intersection of the two parallel lines. So that's a long way to say this is not f1 plus f2. What would it be? Well, just kind of play with, you can either exhaustively try the combinations that you have available, or you could look and say, hey, this would be perfect. This would be f1 plus f2 if f1 wasn't drawn from left to right, if it were drawn from right to left. Because in that case, the tip would be over here, and it would be aligned with the tail of f2. We'd have tip to tail arrangement, and that would be our resultant. So how would we make that scenario happen? Well, we just need to rotate f1 by 180 degrees, which we can do by multiplying by -1. So this resultant is minus f1 plus f2. Another way you could write that is f2 minus f1, but of the options that are available, you'll notice that that first is what's actually shown as an answer. So hopefully this makes sense. Key points are: remember your scaling rules, what happens when you scale by a negative, what happens whether the scaling factor has an absolute value greater than 1 or less than 1, along with the two geometrical definitions of the parallelogram rule and the triangle rule, which kind of give us a basis for understanding vector addition although we're not going to use it because it's mathematically cumbersome.